about 180, that seems to be our sweet spot. I'll stop it there. It's about 45 seconds, a minute at the most to do a calculation like that. All right, let's stop it there. Again, super nice tight consensus on C. You see it. And C it is. So that's easy, right? We've got a number versus 100. Size of reproductive population was 1,000, 10%. So the birth rate there is 10%. Let's look at the opposite of that. So let's take a look at death rate or mortality. Is the norm in our world to live to old, ripe age and then keel over from natural causes? No. We are a rarity in that. All right? That is not the norm. Most organisms do not die of ripe old age. They get eaten, they get sick. It's a pretty vicious world out there. And so how do we calculate this? Q sub x is a function of d sub x divided by n sub x. What does that symbolically represent? Per capita death rate is a function of the number of deaths, and notice again, size of population at risk. So it's not the total population, it's how many are at risk. We just talked about that school of fishes, right? Not all of them are really at risk. If I'm dead center, my risk is negligible, hardly anything. So here's an example. I have a population of zebras. That zebra population is 1,000 individuals, and there's 10 deaths within that population. So the population of zebras at risk is 1,000. How do I calculate that? Well, here's my predator. Is that zebra at risk? Yes. If my head is in crocodile jaws, I'm at risk, okay? You're like, I don't know. Yeah, it's risk. Big time risk, okay? So here's the thing. While I'm standing on dry land, what's my potential risk to this? Hardly anything. The further away I get from the river, it goes down to 0. But I have to cross the river in migration. So that means now I'm at risk. As soon as I touch that water or get near it, I'm at risk. So not all animals are at risk at all times. So in this case, tell me what the death rate of the zebra population is. If your population at risk is 1,000 and you have 10 deaths. All right, you guys crank right through that one. We're right next to 180. Please put your answer in. Can you give me the 180? One person. Come on. Seriously. 180. Not going to give it to me, huh? That's just rude. All right, let's stop it. Let's see what we got. Okay, there's really nice tight consensus on 92. There's a little bit on C though, so go back and check your mathematics a little bit, get an understanding of that in terms of decimal placing. But let's take a peek. And so in this case, is it A? A it is, 10 over 1,000. So we're looking at 1% mortality rate. Now, in this situation, I can do exactly the same thing for immigration and emigration. But you get the picture, right? We don't need to do that, it's just redundant. But that's exactly how I would calculate immigration and emigration. The numbers immigrating for the population that's actually in immigration, that can immigrate. Certain individuals can't immigrate. Same thing for immigration. Not all of them can move. So if that's the case, it would be which ones are available to move in, which ones are available to move out. Do exactly the same calculations. So when we think about immigration rate, the number of individuals moving into a place per unit time, emigration rate is the number of individuals moving out per unit time. Now, there are certain things we can take away from that. The importance of birth and death versus immigration and emigration vary with the spatial and temporal scales of investigation. So typically the way it works is this. The larger the spatial scale gets and the longer the temporal scale, the more important birth and death are to actually affecting the population dynamics, or whether a pop goes up, down, or stabilizes. The smaller the spatial scale gets, typically, the more important immigration and emigration become in determining the dynamics. So here would be an example. Let's say that we have a river, and that river is going from there to there. There's the headwaters of the river, and there's where it ends up in the ocean over there. Now, if I have a fish here, right, and it moves from this site to avoid predation to there, was there any impact globally on the population size? None at all, because I'm calculating from there to there as my population. So if it moves from here to there, there to there, the population size didn't change at all. But what if the scale of my investigation is not the entire river, but it's this little meter piece right here? Now I'm the predator and I walk up and zoop, it moves over. What's my impact right here locally? 100%. It went from 1 to 0. So as my spatial scale got smaller, the importance of immigration and emigration got really big. Let's go back and stretch it out. Now if I have one fish born in this river as a whole, is that a change in the population dynamics? One, yes it was. If I had the accuracy to measure it, I could measure it and calculate it, and the demographics of mortality had a major impact on that population. Whereas if it moved from here to here, did it? It didn't have any impact at all. So that's the difference, and that's a nice generalization. So the bigger the spatial and temporal scales, the more important natality and mortality are. The smaller it gets, the more important immigration and emigration are. We're going to see that movement is really important for how species maintain themselves over time and space, especially when populations are broken into discrete units that are not homogeneous in nature. All right, so we want to go measure a population. I know how to do it now. I know how to count it, subsample it, indirect indicator on it. I know how to calculate a birth rate. I know how to calculate a death rate. I know how to calculate immigration rates and emigration rates. Well, let's go out and do it. So the first thing I need to do is go out and I can make direct measurements of a population's increase or decrease. So I'm interested in the population size of this seal colony over time. I got a problem immediately when I do that. What's my problem? If I want to do this and I'm 60 years old, what's my problem? It's going to take too long. And what does that mean it's going to take too long? What's that? In a way, but what's the problem? I'm 60 years old and I want to measure how this population increases or decreases over time. I don't have much time. I'm going to die before I can figure that out probably, right? Because they're going to outlive me. So if there's a mismatch between the time that I can measure and the time that these guys are living, that's problematic. So if I want a population metric on bristlecone pine trees, well, they're 5,000 years old. Am I going to be able to do that? No, it's outside my realm as an individual to do that. So direct observations are great because they're accurate in time and place. The problem is I can't get at it because they're too long-lived often. Well, again, we start doing other tiers down. I can do an age structure. Okay, they outlived me, but they won't outlive me, you, and you down the line, right? And we can take all that information and add it together to create age structures. And when you do that, you notice that organism populations typically fall into three main types. When you look from their percent survivorship over their life stage from young to old and when they die. So a type 1 looks like this. We fall within a type 1, and it's actually quite rare. So type 1 means that once you're born, your odds of survival are amazingly high. Okay? And you will live to a ripe old age before you die. Now, this is different around the world depending on where you live. You're born in America or a developing nation in the world, you're going to live. The odds of survival are super high. But if you're born in a developing nation in the world, someplace in the outback without medical care, whatever, you can die. And so it's not quite as firm a relationship. But on average, human beings show this as a whole. Now, some of you are going to die by sheer chance advance. Unfortunately, that's just life. It happens. It's not happy, but it does. But most of you are going to live to be ripe old age, and then when you get into your 80s, like I can't remember what the average age of death in America. It's dropped recently because of a lot of things, stress, pollution, and mostly eating habits, right? It used to be going up, 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 and now it's actually dropped down quite a bit. Other nations of the world are still in ascent. I think ours is around 78, something like that. There's other areas of the world that are pushing into the 80s now, which is pretty impressive, okay? But eventually you shut down. You just die. You're going to fall off the map. Then we have birds. Birds are really interesting because birds from the moment that they're born to the moment they die have about the same mortality rate. Mostly because they're hardwired. They know a lot of stuff right when they come out. So their survivability is pretty high. They don't have to learn anything. So what you see is this linear decrease, where this rate of death is pretty much consistent from the moment they're born to the moment they die. And then there's this last one, which is type 3. Certain plants and fishes display this. What does it mean when you're born? What's your odds of survival? They're really low. So the vast majority of you are going to die. If you're, like a nice example of this in terms of fish would be bluefin tuna. So bluefin tuna, when they're born, they die by the thousands, millions, right? They're dead. They die off quick. But once you get to a certain age, you're almost completely invulnerable to anything in the environment. You live forever. So they can live a long time. I don't even know how bluefin tuna, 100 years, something crazy like that. Bluefin tuna go on and on and on and on. Why? They don't have any predators except us because they get too big. They're faster than anything in the darn ocean, right? And they can eat anything that they can find. So they're basically, you know, impermeable to death at a certain point, and if they get a disease or something, and they're really hardy fishes. An example in terms of plant would be a sequoia tree. When they first germinate, they're this big. What's their odds of survival? It's almost nil. But once you get to a certain size, your bark is this thick, you're this high, nothing can touch you, fires can't burn you, diseases can't get at you. The only thing that can get at them is us again if we chop them down. And they can live for 1,000 years. So that's an example of a type 3. Once you get to a certain point, you live a long time, right? Us, we all live relatively well, but then we die quickly at the end. Birds kind of right in the middle. So those are basically age relationships that are determined from multiple generations of us, multiple people looking at these organisms over time. All right? Sometimes even that doesn't work. And if that doesn't work, you're left with mathematical constructs to get at predictions. So they view populations at really fundamental levels. And basically, the results of these models are fairly general, depending on how they're constructed, and you can apply them to lots of things. The more specific a model gets, the more precise its measurement will be, but the less applicable it is to other things. It only measures one thing very well. So generalized models are nice because they measure lots of things. All right, so this is really great for measuring populations that are too long-lived. They outlive us. We can't have a great way to measure whether they're going up or down, and we can make some really nice predictions from mathematical constructs. So let's talk about biological dynamics again, the patterns of change and growth of biological systems over time and space. So we force you guys to take calculus, right? And you're like, why the hell do I have to take calculus? Well,